Okay, so today we're going to work on finding the length of curves in space. And I want you to remember we have found arc length before, but we did it for two-dimensional curves. And one of the key developments in coming up with that formula was to use the Pythagorean theorem. And that was easy for triangles in the plane, but there's a very similar formula for length of line segments in three-dimensional space. So I want to talk about that first. So let's just draw up one of our XYZ axes. And let's say that we want to know this length here. So how do we do it? Well, what we're going to do is we're going to drop this guy down into the XY plane. Make a right angle here. We'll call this length delta z. And what we can notice now is in order to get to this particular point, we have a right triangle here with length delta y and other side length delta x. So the nice thing is now we can find this intermediate length, we'll call it s, and we know from the Pythagorean theorem for that length s, we have that s squared is equal to delta x squared plus delta y squared. We also know from looking at the other triangle, the one here with side length delta x, or delta z and s, that this actual length that we care about looks like this. And so just simply substituting in for s squared gives us this formula. And we can now take the square root of both sides, and we can show that this length L here is just square root of delta x squared plus delta y squared plus delta z squared. And so if we know the change in x, the change in y, and the change in z, we have something that looks very, very similar to our Pythagorean theorem. And this formula is going to play a key role in our developing of the arc length formula for curves in 3-space. Okay, so now that we know how to find the length of a line segment of a line in three-dimensional space, what we really want to do is figure out, well, how do we find the length of a segment of a curve? So in order to do this, let's first look at a curve. And let's ask the following question. So we'll pick a point on this curve, say point A, and another point, point B. And we're going to ask ourselves, what is the length of this curve segment from A to B? So how do we go about doing that? Well, one of the complications now is that we need to describe this curve as a vector-valued function. So what we're really going to do is we're going to start with the description, or the parameterization of this curve. This will maybe be given, maybe you have to figure it out, but we really want to try to describe this curve in terms of a vector-valued function, and we have to tell you then what value of our parameter t corresponds to point capital A and point capital B. So this will be when t is equal to little a, this will be when t is equal to little b. And so now we want to, we have to work with that parameterization, whether we want to or not. So how do we go about doing that? Well, in order to find this length, we're going to use a familiar procedure. So what we did before was we would slice the curve up. So we will pick a couple points on that curve. And then what do we do with those different slices? Well, we approximate them. And what should we approximate them as? Well, we just talked about finding lengths of line segments. Each of those segments looks like a line segment. So each slice here is approximately a line segment. So I'll draw that on our picture. Just as before, this actually doesn't look like it does a terrible job, but just as before, the more slices we use, the better approximation we get. And so what we want to do now is actually pick one of these slices. So I'm going to pick this one right here. And we're going to say that this guy has length delta s. So how do we know what that is? Well, we just came up with a formula for it. If I know what the x, y, and z coordinates are at my point here and my point here, I can calculate the difference between them, and I can then calculate my delta s as the square root of delta x squared plus delta y squared plus delta z squared. So that's nice. Then once we have that, that approximation, we can integrate. But what we write down here, so this s is supposed to be, we're supposed to add up all of these slices. So we simultaneously shrink these slice lengths to 0. But we have to add up all infinitely many of them. And that's done by a definite integral. But the problem is, if you actually look at this, I'm going to write all slices there, because what the heck does this integral even mean? I mean, we're thinking of it conceptually as trying to add up all of these slices, but do we have any control over what delta x, delta y, and delta z are whenever these things get small? Well, not really. So it is certainly still true that we will indicate that these finite slices become infinitesimal by changing these deltas to d's. Normally I'd just write that down originally, but it's probably been a while since you've seen the formula, so I want to remind you that that indicates the limit that these slice widths are all shrinking to 0. And the integral is represents the limit of adding all of them together. So in order to go from here, we have to figure out how do we describe this delta x, delta y, delta z, and in turn dx, dy, and dz. So how should we do that? Well, we have a parameterization of this curve, r of t, and we can use that to express the x, the y, and the z in terms of t. So if we actually look at this r of t, we would actually see a vector here, and what you're supposed to be getting in the habit of doing is realizing that whenever we write this down, the first component describes the x position in space in terms of the parameter t, the second gives y in terms of t, and the last gives z in terms of t. So we can really think here that x, y, and z are functions of t. And that's nice because we know exactly how to relate the differential dx to the differential dt. In fact, we know here that my dx, it's really just the derivative of x with respect to t times dt. The differential dy is just y prime of t dt. And same thing goes with z. So this is nice because it now allows us to write dx, dy, dz in terms of t. And we now can have this arc length described entirely in terms of our parameter. And so that allows us to write down the arc length formula. It'll be the integral from t equals a to t equals b. It'll capture all of the slices from t equals a to t equals b. And then all we really have to do here is substitute in for our differentials. Which is not hard to do. And the nice thing now is that, oops, I have to square this last one. The nice thing now is that we can simplify this. So after a little bit of algebra, just square out each of these. Each of them will have a dt squared. And so what I can now write here is an x prime of t squared plus y prime of t squared plus z prime of t squared. And all of this will be times this dt squared. But we know that if we have this product underneath the square root, we can look at the square root of a product as the product of the square roots. And so what I can do is I can take this and write it much more simply by just using that rule. So by doing that, I'm not going to write the whole thing out again, but we obtain exactly this formula. And so, I'm going to comment on this in a second, but we now have expressed dx, dy, and dz in terms of our parameter t, which is nice because we have limits of integration for that. And we also have an integral that just has one variable in it, which is the entire goal. This integral at the top here, I mean, conceptually, it tells us the right thing to do. We're going to add up all of these little slices, but we have to figure out, well, how do we actually do that? So while this top one is maybe useful conceptually, or at least captures the process, this bottom one here actually allows us to do the computations that we're going to need to do. But before we do those computations for a specific example, I want to talk about a much nicer way to write this formula that also gives us a different vantage point. Okay, so we want to try to reimagine this formula in a little different way. So one thing that we can actually ask is, well, what is this? What's this expression down here? So one thing, remember, we started with this r of t. Let me say, remember. This r of t, we list the x, the y, and the z. And we can actually express this in terms of r. So how do we get that? So I actually want you to take a couple minutes to yourself and ask, is this related to something we know about r? Okay, so we have an x prime of t, a y prime of t, and a z prime of t. Well, so one thing that we can do is if we would actually take a derivative of r, we note that this r prime of t would just look like that guy, right? And one thing that's sort of nice about that is if we look at the magnitude of this, what happens? Well, how do we find the magnitude of any type of vector? Well, we square the first component, we square the second component, and we square the last component. And that should look very familiar because it's exactly the expression inside of this integral. And so that allows us to actually write this in a little bit different way. So instead of writing that whole thing out, what we can really do is we can just rewrite this formula like that. And so there's something interesting here. This original formulation up here at the top, we got that from a pretty geometric argument. We used the Pythagorean theorem, and we said we're going to just add up the length of all of these line segments. Well, one of the interesting ways of thinking about a parameterized curve is we know what the curve looks like, but the parameter also gives us a way to trace the curve out. And so it's sort of natural to think of this t as a time parameter. So what does that tell us? Well, that tells us that this is just the magnitude of the speed. This thing here is a change in time, small change in time. So what's speed times a little bit of time? It's a little distance. So this thing here, distance, change in distance, this thing here, this inside expression, actually represents a small distance along the curve. And so now we can think of this as we're going to go small distances along the curve from time A to time B and add all of them together. And what do we expect to get if we do that? Well, we expect to get the distance that we've traveled along the curve. So this top one gives us a very geometric argument based on the Pythagorean theorem. This bottom way actually allows us to reinterpret the arc length in terms of our original time parameter in a more physical kind of way. So you can think about it either way you want, but it's nice to have both of these vantage points.